With today's video, we begin a new unit, Unit 10, Polynomial and Rational Functions. We'll be covering pages 258 to 260. You want to have your graphing calculator and a highlighter. Lesson 1, we look at an introduction to power functions. The power function is a function of the form f of x equals a times x to the b. A and b do not equal 0. As a warm-up, for each of the following power functions, state the value of a and b by rewriting the equation in the form y equals a times x to the b. Y equals 3 over x squared. We don't want x squared down in the denominator. Rather, we want our variable x as a base up in the numerator. So if we take this and bring it up to the numerator, recall what happens. That's equivalent to 3 times x to the negative 2. In which case a would equal 3 and b equals negative 2. For b, y equals 1 over 7x to the third. Just the x to the third needs to be pushed up. The 7 stays where it is. Y equals 1/7 x to the negative 3. A equals 1/7, b equals negative 3. C, y equals 8 times the square root of x. Square root of x, recall, is equivalent to what exponent? What fractional exponent? 1/2. A equals 8, b equals 1/2. And D, y equals 6 over the cube root of x. Two things. We will first want to express the cube root with a fractional exponent, 1/3, and then to move it up, that is 6x to the negative 1/3. Y equals 6x to the negative 1/3, a equals 6, b equals negative 1/3. The characteristic of power functions depend on both a and b, the most important being the b value, the exponent. Consider the power function y equals a times x to the b. What is the y-intercept of the power function if b is greater than 0? So for a y-intercept, the x-coordinate of a y-intercept is 0. Let's take our equation y equals ax to the b and replace x with 0, and our b value has to be something greater than 0, so it has to be positive. I can put a 10 in there, I can put a 1, it doesn't matter. 0 to any power is still 0. A times 0 is going to be 0. The y-intercept is the origin. As long as the power is greater than 0, the y-intercept is going to be the origin for a power function. What can be said about the y-intercept of a power function if b is less than 0? We're still looking for y-intercept, so we replace x with 0. And let's say I put negative 2, or negative 1, or negative 10 in for b. Well, to take care of the negative, we would bring this down into the denominator with a positive exponent, but 0 squared is still going to be 0. A over 0 is undefined. So a y-intercept does not exist. So if b is less than 0, the y-intercept does not exist. Sorry about that. we will concentrate on power functions where the exponent is a positive whole number. So that will be the focus for the rest of this portion of Unit 10. Fill in the following table with values for common power function y equals x to the b. So we have an x value of -3, so -3 squared is 9. -3 to the power of 3 is -27. -3 to the power of 4, positive 81. -3 to the power of 5, -243. Next, 3 squared, 9. 3 to the power of 3, 27. 3 to the 4th, 81. 3 to the 5th, 243. Substituting -2 in for x. -2 squared, 4. -2 raised to the power of 3, -8. -2 to the 4th, 16. -2 to the 5th, -32. Positive 2 squared, 4. Positive 2 raised to the 3rd, 8. Raised to the 4th, 16. Raised to the 5th, 32. -1 squared, 1. -1 cubed, -1. Raised to the 4th, 1. Raised to the 5th, -1. Positive 1 squared, 1. Positive 1 cubed, 1. 4th, 1. 5th, 1. And 0, whether it be squared, cubed, or raised to the 4th or 5th, is still 0. We see here when the exponent is odd, positive and negative inputs give opposite outputs. If the exponent is even, positive or negative inputs give same outputs. And that, I believe, is typed out for us on the top of the next page. Yes, from the previous exercise, note when the power function has an even exponent, the positive and negative inputs produce same outputs. When the function is odd exponent, the positive and negative inputs produce opposite outputs. Use a graphing calculator to sketch the power function below using the standard window. Y equals x squared, we know what that looks like. And, well, I might as well erase the rest and put it in. Okay, so y equals, that's our parabola. Y equals x to the power of 3. To the power of 4. Looks like a tighter x squared. And then to the power of 5. Now what we notice here is that with our odd powers, if we have an odd exponent, the ends, or the tails, ends and tails are referring to the opposite ends of the graph. Odd exponent, tails point in opposite directions. This is something you're going to have to memorize. Whereas if we have an even exponent, the tails point in the same direction. Right? The tails point in the same direction when you have an even exponent. It's important to remember this. Which of the following power functions is shown in the graph below? Explain your choice. Do not use a calculator. All right, so first off, the tails point in the same direction here. So the exponent is even. So it's either choice 2 or choice 3. And if we look back at 4A and 4C, the leading coefficient was a positive 1, and both tails pointed upward in the same direction. Well, here these tails point downward, so that means the leading coefficient is negative. So let's add that. Or in which case you can just look at the right tail. The right tail falls, it's going down to negative infinity. If your right tail falls, then the leading coefficient is negative. The right tail falls, so the leading coefficient is negative. So it is choice 2. The end behavior of polynomials, we're not going to go through this, but the end behavior of polynomials, as x value gets very large, as x goes to positive infinity or negative infinity, it's important to understand that the end behavior of a polynomial, whether it rises or falls right, is controlled by its highest powered term. It's controlled by the highest powered term. So in exercise number 6, when it says consider two functions, or consider the polynomial function f of x equals x cubed minus 2x squared minus 29x plus 3, you find the highest powered term, which is this. So whatever the power function y equals x cubed looks like, that's what this polynomial function graph would look like. In which case it is going to, the leading coefficient is positive, so the right tail rises. So we say rises right because of the leading positive. Working. Leading coefficient's positive, so it rises right. The exponent is odd. Tails point in same direction. Sorry, tails point opposite direction. this here, this is going to overpower every other term, okay? That term with the highest exponent will overpower every other term in the polynomial function, so it is going to closely resemble the power function y equals x to the power of 3. Exercise 7, sketch the general shape of a power function given each of the following criteria. Fill in the end behavior of each. As x goes to positive infinity, what do the y values approach? And as x goes to negative infinity, what do the y values approach? Here it is, starred. If A, the leading coefficient, is positive, the right tail rises. If A is negative, the right tail falls. If B, the exponent or degree, is odd, the tails point in opposite directions. If even, the tails point in the same direction. Okay, y equals ax to the b. If A is positive, the right tail rises. Right tail rises. A is positive, right tail is going to rise. B is odd, the exponent is odd, so the tails point in opposite directions. As x goes to positive infinity, y is also going up to positive infinity here. As x goes to negative infinity, we're going off this way. As x goes to negative infinity, y goes to negative infinity. If A is positive, the leading coefficient is positive, the right tail rises. If B is even, that means the tails point in the same direction. If the exponent is okay, so that means this also goes that way. Now the tails are pointing in the same direction. As x goes to positive infinity, y is also going to positive infinity. As x goes to negative infinity, y is going to positive infinity. Y equals ax to the b. If A is negative, that means the right tail falls. A is negative, that the leading coefficient is negative, right tail falls. Like this, right tail is falling. B is odd, the tails point in opposite directions. Okay, so that means the left tail goes this way. As x goes to positive infinity, y is going to negative infinity. As x goes to negative infinity, y is going to positive infinity, or going upward. If A is negative, we know the right tail falls. If B is even, we know that the tails point in the same direction, so that means the left tail must also fall. As x goes to positive infinity, as we follow out here, our y is going down to negative infinity. And as x goes to negative infinity, y also is going to negative infinity. Exercise 8, identify which of the following are power functions. For each power function, rewrite it in the form of y equals ax to the b. Okay, so let's simplify this here. This would be be equivalent to y equals 6x to the 4th, and this is a power function. This is not a power function. This would be a polynomial function. Y equals 5 divided by x to the 4th. Let's rewrite this as y equals 5 times x to the negative 4. This is a power function. Square root, well, let's see. Square root of 36 is 6. Y equals 6. X to the 9th, I'm going to write that, or sorry, the square root of x to the 9th, I'm going to write as x to the fractional exponent 9/2. And that's real. So our a and b values are real numbers. This is a power function. For each of the following polynomials, write a power function that best represents the end behavior of the polynomial. It's going to be the term with the highest exponent. So the term with the highest exponent, the power function it would resemble is 6x to the power of 4. B, the term with the highest exponent. So this polynomial function would resemble, y equals negative 5x to the power of 3. And the term with the highest exponent, this graph would resemble y equals 9x to the 8th. This exponent, right, is known as the degree. So this would be considered degree 8. This would be degree 3. And this would be degree 4. Thank you for your attention.